Volcanic eruptions can cause widespread devastation to surrounding environments. Ash clouds from volcanic events can block sunlight, leading to significant environmental changes. The immediate aftermath of a major volcanic event includes the deposition of ash and debris across vast areas. Volcanic eruptions release tremendous energy, reshaping landscapes and impacting ecosystems. The destructive potential of volcanoes stems from the combination of heat, pressure, and ejected materials. Volcanic eruptions involve the release of molten rock, known as lava, onto the Earth's surface. The scale of volcanic eruptions can vary significantly, ranging from small lava flows to massive explosions. Lava rivers can cover vast areas, reshaping the landscape and impacting surrounding ecosystems. The intensity of volcanic eruptions is influenced by factors such as magma composition and gas content. Volcanic eruptions can have significant environmental and climatic effects. The central question explores how life managed to survive catastrophic volcanic events throughout history. Understanding survival mechanisms requires examining geological records and biological adaptations. Volcanic eruptions drastically alter environments, posing extreme challenges to living organisms. Investigating these events provides insights into the resilience and adaptability of life on Earth. Continental collision leads to the formation of extensive volcanic regions. The immense pressure and heat from colliding plates generate massive magma chambers. These magma chambers eventually erupt, creating large, igneous provinces like the Siberian Traps. The Siberian Traps are characterized by vast outpourings of basaltic lava over a prolonged period. These eruptions release massive amounts of greenhouse gases into the atmosphere. The release of greenhouse gases triggers significant global climate change. The Siberian Traps eruption released massive volumes of molten rock across vast areas. The eruption caused the sky to turn red due to the extensive ash and particulate matter. The scale of the eruption covered significant portions of the Earth's surface. The lava flows dramatically altered the existing landscape. The eruption released significant quantities of greenhouse gases into the atmosphere. The Siberian Traps eruption is considered one of the largest volcanic events in Earth's history. The Permian-Triassic extinction event, also known as the Great Dying, represents the Earth's most severe known extinction event. This catastrophic event resulted in the extinction of approximately 96% of marine species. Terrestrial life suffered immensely, with an estimated 70% of land vertebrates disappearing. The Permian-Triassic extinction dramatically reshaped the course of evolution and the composition of life on Earth. The eruption of Mount Tambora in 1815 was a significant volcanic event, causing widespread global impact. Super eruptions, such as the Siberian Traps, dwarf even events like Tambora in terms of scale and environmental consequences. The Siberian Traps represent a series of massive volcanic eruptions that occurred over a prolonged period. The environmental impact of super eruptions includes significant climate change and widespread extinction events. Understanding the scale of super eruptions helps to contextualize the potential risks associated with future volcanic events. Mount Tambora's eruption triggered widespread global famine due to climate disruption. Atmospheric ash clouds from the eruption caused dramatically altered, blood-red skies worldwide. Volcanic activity directly resulted in immediate consequences, such as crop failure and livestock death. The eruption's impact extended beyond immediate devastation, causing long-term ecological and societal disruption. Global food supply chains were severely impacted, leading to widespread starvation and disease. Volcanic activity played a crucial role in the early formation of Earth's atmosphere. Volcanoes release gases, including water vapor, carbon dioxide, and nitrogen, from the Earth's interior. These volcanic gases gradually formed the early atmosphere, essential for the development of life. Volcanic outgassing provided the building blocks for the oceans in a more temperate climate. Volcanic outgassing released substantial amounts of gases from the Earth's interior. The continuous release of water vapor from volcanoes gradually formed the Earth's oceans. Volcanic emissions also contributed significantly to the creation of the early atmosphere. The early atmosphere, rich in volcanic gases, differed significantly from today's atmosphere. This process of volcanic outgassing was crucial for the development of life-supporting conditions on Earth. Earth's climate undergoes cyclical shifts between greenhouse heat and freezing conditions. Volcanic activity is a key driver of these dramatic climate swings. Periods of intense volcanic eruptions lead to increased greenhouse gases and global warming. Conversely, prolonged volcanic winters can plunge the Earth into freezing darkness. The balance between these opposing forces shapes Earth's long-term climate patterns. Understanding these climate cycles is crucial for predicting future environmental changes. Volcanic eruptions release large quantities of ash and gases into the atmosphere, initially causing a warming effect. The emitted sulfur dioxide forms sulfate aerosols, reflecting sunlight and leading to a cooling effect. Over time, the cooling effect can dominate, potentially triggering or exacerbating ice age conditions. The balance between warming and cooling effects determines the overall impact of volcanic activity on global climate. The cyclical nature of volcanic eruptions contributes to long-term climate variability, including periods of extreme heat and ice ages. Volcanoes serve as the Earth's natural safety valves. Volcanic activity releases internal pressure, preventing more catastrophic geological events. The Earth's internal pressure necessitates periodic volcanic eruptions. Volcanoes are an integral component of Earth's dynamic system. The Hawaiian Islands are formed by volcanic activity over a hotspot in the Earth's mantle. As the Pacific Plate moves, successive volcanoes are created, forming a chain of islands. The islands increase in size through continuous lava flows, both above and below sea level. Erosion gradually wears down the older islands, reducing their size and complexity. Submarine landslides and subsidence also contribute to the reshaping of the islands over millions of years. The Hawaiian Islands represent a continuous cycle of creation and destruction driven by plate tectonics and volcanic activity. Volcanic environments present extreme conditions, requiring unique adaptations for life to thrive. Extremophiles, such as thermophilic bacteria and archaea, exhibit remarkable resilience to high temperatures and toxic chemicals. Evolutionary adaptation allows organisms to develop specialized traits for survival in volcanic habitats. Life in volcanic areas demonstrates the resilience and adaptability of organisms in the face of environmental challenges. Extremophile bacteria are microorganisms that thrive in extreme environmental conditions. These organisms can survive in environments such as boiling hot springs, which would be lethal to most life forms. Extremophiles have unique cellular adaptations that allow them to withstand high temperatures. Specialized enzymes and proteins maintain stability and functionality at extreme temperatures. The ability to survive in extreme conditions makes extremophiles valuable in various biotechnological applications. Researching extremophiles provides insights into the potential for life in other extreme environments, such as on other planets. Volcanic ash provides a nutrient-rich foundation for ecosystem rebuilding. The regenerative properties of volcanic materials accelerate plant growth. Pioneer species colonize the volcanic ash, initiating the process of ecological succession. The breakdown of volcanic rock releases essential minerals, enriching the soil. Ecosystems rebuild on volcanic ash through a gradual process of ecological succession. Volcanic ash enriches soil by depositing essential minerals. The weathering of volcanic rock releases nutrients vital for plant growth. Volcanic soil's porous nature enhances water retention, benefiting plant hydration. The high mineral content in volcanic soil supports rapid ecosystem recovery after eruptions. Volcanic ash acts as a natural fertilizer, promoting vigorous plant growth. The unique composition of volcanic soil fosters specialized plant communities. Geothermal energy is a sustainable energy source derived from the Earth's internal heat. Volcanic activity provides a significant source of geothermal energy. Geothermal power plants harness this heat to generate electricity. Harnessing geothermal energy reduces reliance on fossil fuels and lowers carbon emissions. Volcanic activity facilitates the formation of valuable mineral deposits through hydrothermal processes. Magmatic fluids release dissolved metals, which precipitate as ore deposits upon cooling and interaction with surrounding rocks. Sublimation of volcanic gases near vents leads to the direct deposition of certain minerals, such as sulfur. Volcanic regions are economically significant due to the presence of these mineral deposits, supporting mining industries. Erosion of volcanic rocks releases valuable minerals into streams and sediments, forming placer deposits. Volcanic eruptions can lead to the formation of new landmasses. Lava flows contribute to the expansion of coastlines. New volcanic land provides opportunities for the creation of new habitats. The process of volcanic land formation involves the cooling and solidification of molten rock. Volcanic activity can reshape existing landscapes and create entirely new geological features. The mineral-rich volcanic soil supports the growth of unique ecosystems. Volcanic monitoring involves the use of advanced technology to predict potential eruptions. Seismographs detect subtle ground movements, providing early warnings of increasing volcanic activity. Gas sensors measure the concentration of volcanic gases, such as sulfur dioxide, which can indicate an impending eruption. Thermal cameras capture infrared images, revealing temperature changes that may signal magma movement. Data from various sensors are integrated into predictive models to assess the likelihood of an eruption. Effective monitoring and prediction can help mitigate potential disasters by enabling timely evacuations. Evacuation plans are a crucial strategy for mitigating volcanic hazards and ensuring public safety. Infrastructure protection involves reinforcing buildings and critical facilities against volcanic impacts such as ashfall and lahars. Monitoring volcanic activity through seismographs and gas sensors allows for early warnings and timely evacuations. Lahar control structures, such as dams and channels, redirect and contain destructive mudflows. Public education campaigns increase awareness of volcanic hazards and promote effective responses during eruptions. Supereruptions are rare, but potentially catastrophic geological events. The consequences of a supereruption include widespread ashfall, climate change, and ecosystem disruption. Geological monitoring and research are crucial for understanding and potentially mitigating the risks of future supereruptions. Understanding the dynamics of magma chambers is key to predicting the likelihood and magnitude of supereruptions. Volcanoes continue to play a significant role in shaping Earth's future. Volcanic eruptions pose ongoing threats to human populations and infrastructure. Volcanic activity also contributes to the formation of new land and enriches soil fertility. Geothermal energy, harnessed from volcanic regions, offers a sustainable power source. Volcanic gases influence atmospheric composition and global climate patterns. Understanding volcanic processes is crucial for mitigating risks and harnessing potential benefits. If you enjoyed this journey through Mind Jungle, make sure to subscribe and join us for more mysteries of nature, history, and the world around us.